Welcome to this new module on numerical simulation in the sports field. Here, we will explore how computational tools such as finite element analysis and computational fluid dynamics can be applied to study materials, optimize product design, and enhance athletic performances. In the rapidly evolving world of sports equipment and apparel, understanding and optimizing material properties is paramount to enhance athlete performances, comfort, and safety. Traditionally, this process has heavily relied on extensive laboratory testing, involving the creation of physical prototypes and a series of experimental evaluations. While invaluable, these empirical approaches are often time and cost-consuming, requiring significant resources for material procurement, manufacturing, and repeated testing cycles. These present a challenge particularly when exploring a vast range of material compositions, structural variation, or design modification. However, a new frontier in material development has emerged with the advent of numerical simulation. At its core, the finite elements analysis, or FEM, works by discretizing a continuous domain into a finite number of smaller, simple geometric units called finite elements. Within each element, the governing equation as equilibrium equation for structural analysis are approximated using interpolation function. These element-level equations are then assembled to form a global system of equations, which is solved to determine the behavior as displacement, stress, or temperature at discrete points across the entire domain. This allows engineers to analyze structure with intricate geometries, heterogeneous material properties, and complex loading conditions. The first two examples we will explore in numerical simulation for sports revolve around the computational fluid dynamic, CFD, applied into distinct adaptation. Firstly, CFD can be employed for the study of air permeability and the potential modeling of multi-phase system for moisture management analysis. Let's consider, for instance, the creation of a technical fabric for a t-shirt. As we have discussed in the previous modules, to ensure user comfort, such a fabric must possess excellent air permeability and superior moisture management properties. In this context, CFD allows us to virtually manipulate and vary key design parameters that are directly controllable during the manufacturing phase. These include variables like the warp and the weft threads density, the effective yarn diameter, and the wave type for the fabric, or its overall thickness. By simulating these changes, we can observe their precise impact of the final product's performance. This capability introduces a crucial preliminary phase before physical prototyping, enabling the optimization of the product a priori to its actual production, thereby bypassing often costly and time-consuming laboratory testing. Secondly, the same CFD principle extends to moisture management. Here, we can model a complex multi-phase system composed of air and water vapor. Through such simulation, we can observe the interaction of the system with individual textile fibers and the fabric as a whole. This insight allows for the optimization of design parameters specifically aimed to enhance moisture transport and the overall comfort, without the need for immediate physical fabrication and testing. A further compelling application of computational fluid dynamics lies in the study of transport phenomena involved in the thermal exchange of a complex system, such as a boat, for instance, operating in a cold and hostile environment. In this context, CFD enables a highly granular and predictive analysis of the boat's thermal behavior. engineers can model the coupled heat transfer between the foot, the various layers of the boot's material architecture, like liner, insulation, and shell, and the surrounding external environment. This involves material property integration, simulating the impact of diverse materials, each characterized by its specific thermal conductivity, heat capacity, and density on the overall thermal resistance of the boot system. This helps for a precise understanding of how each material can contribute to the global energy balance of the foot-boot system. Another factor are the environmental boundary conditions. Applying various environmental parameters as a boundary condition to the CFD model allows to simulate the effect of varying wind speeds, like in forced convection, over the boot's outer surface, quantifying localized heat transfer coefficient and the resultant convective heat loss, analyzing the impact of different external ambient temperatures, and then modeling the conductive heat transfer between the boot's outsole and various ground type defined by the thermal conductivity and temperature profiles. Crucially, CFD enables to the discrimination of the contribution from different heat exchange mechanisms: conductive, convective, and radiative. This detailed breakdown provides manufacturers with an invaluable insight, allowing them to precisely identify critical areas within the boot's design or specific environmental factor that disproportionately affect thermal performances. Armed with this knowledge, they can then pinpoint exact area and factor of improvement, leading to more effective and safer footwear design. Beyond fluid dynamics, numerical simulation for sports heavily leverage the finite element method as a powerful numerical technique for solving complex engineering problems. FEM is particularly invaluable for analyzing the distribution of stresses and deformation within sports equipment and understanding how different materials impact the biomechanics of athletic movement. For instance, it can be useful to understand how the racket deforms and where stresses concentrate during the impact within the ball or under dynamic swinging loads. A detailed 3D models of the racket, including the frame, the strings, and handle, must be created. Different materials as carbon fiber composites, fiberglass, and resins are assigned their respective anisotropic material properties, like Young's modulus, Poisson ratio, shear modulus in different directions. The mesh density is often refined in critical areas like the throat and the string bed interface, where stresses concentrations are expected. Boundary condition simulates the player's grip and the impact forces from the ball. Then, FEM provides stress contour plots illustrating areas of high mechanical load, deformation map showing how the frame flexes, and model analysis to identify natural frequencies and vibration modes. This allows manufacturers to optimize the composite layup, fine-tune the frame geometry, and select the specific materials to enhance power, control, reduce unwanted vibration, or improve durability, and all before committing to extensive physical prototypes. Another case could be to understand how the choice of materials within a running shoe influence load transmission, energy management, and the runner's biomechanical response during gait. Crucially, detailed material models are employed, such as non-linear elastic or viscoelastic models for foams, to capture the compression and rebound behavior, and hyperelastic models of rubber outsoles. The interaction between the foot, often represented by simplified or detailed biomechanical model, and the shoe component is managed via contact mechanics algorithm, accounted for friction and pressure distribution. Loading condition can be derived from experimental gate analysis data, providing realistic ground reaction forces. In essence, FEM provides a virtual laboratory where complex physical phenomena can be deconstructed and analyzed with precision, accelerating innovation and reducing development costs in the sports industry. This concludes the module about how numerical simulation can be applied in the sports field, helping product design.